Okay, hello everybody. My name is Marko Paantera, and before going to the actual topic of today's talk, which is ESACOMP, our LAMINATE analysis software, I'd like to give a short overview of the composite design and analysis portfolio in Altair's HyperWorks suite to put ESACOMP in place in this whole scheme. So starting from the requirements and moving through the different phases of concept design, detail design, and design validation, all the way to manufacturing, let's have a look at our solution for the concept design. So the main tool for that part is our FE solver OptiStruct, which has very special optimization capabilities built in. Basically, starting from for composites, we can start from a topology type of approach to find the optimal load paths to carry the loads on the structure, and then go further into designing the ply shapes to be optimal for carrying the loads. In all our simulation that we perform, of course, we need material properties, and for that part, we have a new tool, a multi-scale designer, which is actually the topic of next week's webinar. So we'll get to the details then, and also ESACOMP plays some role in the material model development by providing a materials database, which we will talk about later today. With composites, it's always very important to design something that can be actually manufactured, because you could easily come up with a composite design which is not manufacturable, and so there's no point in doing that kind of design. So there are different aspects like draping that may need to be considered in certain type of structures, and for that we have some solutions, and also we have a solution coming for injection molded short fiber composites. The core of the design of composite structure, and the biggest time is probably spent in detailed design analysis, and then there we have our whole portfolio for finite element analysis, starting from the hypermesh pre-processing using our FE solvers, OptiStruct and Radius being the explicit solver, and then HyperView for post-processing. ESACOMP can play a lot of role in this detailed design and analysis phase, both on the pre-side, post-side, and then also as a sort of independent tool tackling with certain specific issues. Moving into design validation, of course, the goal nowadays is to do as little physical tests as possible and do use simulation as far as possible for the validation. And the more accurate results we want, the more important it will become to have really a good material characterization. And here, multi-scale designer will play an important role. Of course, our core FE tools as well. We call our environment an open architecture platform. And what that means is that you don't need to pick the Altair tools for all these tasks, and of course HyperMesh is very well known product to used widely as a preprocessor for different FE software. Now moving to the actual topic of today's speak, Altair ESACOMP. To define ESACOMP in brief, it can be called a toolbox for composite designers for automating the classical composite calculations. It has a starting point for design. It has an extensive materials database, and most of the analyses are based on the classical lamination theory. Laminate failure analysis, we can usually use first ply failure approach and be able to apply different failure hypotheses. Further, from the laminate level, one can move into structural elements in ESACOMP's panels, joints, and so on. And there are certain advanced capabilities going beyond these typical features, which I will describe a little bit later. Also, ESACOMP integrates with FE analysis on both pre and post side. To give a little bit of background of ESACOMP, already the name ESACOMP refers to the origin as a project initiated by the European Space Agency, ESA. The work started already in the early 1990s, and actually today, this year, ESACOMP has been 20 years in the market as a commercial product. ESACOMP was long known as a product by a company called Componering, but last year, just a little bit over a year ago, Altair acquired then Componering and ESACOMP software, and the ESACOMP team moved to work at Altair. This didn't really come out of blue because ESACOMP had been already available through the Altair Partner Alliance for 5 years, and we had also had technical collaboration between the Altair team and Componering team on integration of ESACOMP and building interfaces between ESACOMP and HyperWorks. So now ESACOMP is available as a part of Altair's HyperWorks suite. Being in the market for 20 years, ESACOMP is used worldwide in all industries utilizing high-performance composites. Aerospace is the biggest user group for us, and also ESACOMP is widely used in the academia for research and educational purposes. The starting point in ESACOMP is usually the homogenized properties of a reinforced ply or core material, from which we then build on to continue to building laminate layups. We have some very a little bit of micromechanics capability to derive the homogenized properties from fiber and matrix properties, but that's not any of the core capabilities of ESACOMP. For that, we have other tools like Multiscale Designer. So starting define material properties from scratch, the ESACOMP user interface guides you by first selecting which kind of material you're defining, if it's a reinforced ply made of unidirectional fibers, or maybe other kind of reinforced ply, or adhesive core ply, or so on. And based on this selection, then the user interface will guide you to define the material properties that are relevant to this particular material. And for instance, if we have defined material to be a unidirectional ply, we usually assume that it's transversely isotropic in the 2-3 plane, and so the user interface will guide you in defining in the plane of isotropy. You only define 2 independent constants, and the third one is computed, as well as if you define the E-modules in the 2 directions, the property in the 3 directions is automatically set as the same. Some of the advanced features in the ESACOMP material definitions include the possibility to define different strength sets. So you can, for instance, define statistically based material strength properties like A and B values used in the aerospace, minimum values or such. It's also possible to define environment dependent properties. So given by the temperature and moisture content and the set of material properties for that environment, ESACOMP can then, when you perform the analysis, it will select the correct material properties according to the given analysis environment, and it can also interpolate between the given values if they don't match the analysis environment. There's possibility to also define statistical data behind any mechanical property of the ply definition, and I will explain later what we use that for. ESACOMP also comes with the material data bank, which has more than 1,000 material systems that come with the ESACOMP installation. This data coming mostly from the material suppliers, so not necessarily something that is that you wouldn't be publicly available from data sheets of the material suppliers, but it's just very practical to have it all readily available as a starting point for design. So there are different types of materials included, starting from adhesives, core materials, fibrous matrix materials, and so on. But the reinforced plies, so the cured ply with the properties of the matrix and fiber in cured form, get from the coupon test. That's the biggest group of data that we have and the typical starting point for most of the analysis in ESACOMP. Of course, end users can also create their own material databases, and of course that's what the users usually do, because the any data that we provide with the material data bank can only be used for initial purposes, for screening the possibilities that there are, but eventually, of course, for composite materials, it's very important that you use the material properties of that really correspond to the actual manufacturing process of that is being used, and nobody can tell those values without some testing. Moving further into laminates, once we have a ply material defined, we can go further into defining a laminate layup, selecting the ply material, defining layer orientations. There are different features in to make this easy. You can use multipliers for substacks and so on. And once we have a layup defined, we can move further into classical lamination theory-based analysis for engineering constants, ABD matrices, expansion coefficients, and so on. You can perform load response analysis for a single laminate, giving us a load case. There's also a possibility to look at the transverse shear stresses. And moving further into failure analysis, performing a first ply failure type of analysis, we can determine the reserve factors or margins of safety, construct failure envelopes. We have wide selection of failure hypotheses that are included in ESACOMP, and you can select from book criterion 2D and 3D versions, LARC criterion, 2 different versions, and so on. Of course, the typical Taibu, Hill, so on, max strain, max stress, and so on. And also, one can define user-defined failure criteria with a Python script. In the part of the failure analysis with the sandwich panel, we always perform determine the sandwich failure modes for wrinkling, core shear, and also we can consider interlaminar shear. Some of the other laminate analysis include, for instance, notch laminate analysis, where an elliptical or circular or elliptical hole is defined in a laminate, and then the stresses and strains around the edge of these notches are computed, and also one can, by applying failure analysis, we can also determine the notch factor. Results, of course, for a single analysis of a laminate can be visualized as layer charts, but further in ESACOMP we have possibility to do multiple analysis, for instance, for several laminates, and then pick up the properties or analysis results of interest, and this way do like make comparisons between different layups or the same layup having different materials used in the laminate and so on and so forth, and it's very nice environment for perform different kinds of trade-off studies this way. Further, there are possibilities to create client charts for, let's say, when the orientation of the laminate is changed. Also, that can be done as a polar chart, or the some layers within a laminate layup can be parameterized as plus minus theta layers, and then graphs can be created for that. Also, carpet plots for plies for screening what kind of properties can be achieved from a certain ply material by combining the 0, 90, and plus minus theta layers in different proportions. Moving into structural elements, typically, well, we start from a laminate layup that has already been defined, and then we define a few geometry parameters defining these structural elements. So in case of a rectangular panel, we give the dimensions in 2 directions. If you want to do a curved panel, we also give the radius of curvature, and we can further define stiffeners in the panel actually in 2 directions, in the X and Y direction, and all these stiffeners can be freely spaced in and given by their location. The stiffener cross section is defined first as a separate object, which is of course also built from a laminate layup and giving dimensions of the cross section. The other type of structural elements that are covered in ESACOMP are beams, cylindrical shells, bonded and mechanical joints. As you may guess, if we go to a panel analysis, we use finite elements to solve this problem, and for that we have an integrated FE solver with ESACOMP. Types of results that we get from the analysis are typically load response, so stresses and strains, deflections, failure analysis, giving reserve factors or margin of safety, and also we can always look into the details of certain location, certain element, and have a closer look on the failure modes and critical layers. We can do buckling analysis and also natural frequencies for panels and cylindrical shells. Some of the advanced analysis capabilities which go beyond the typical classical lamination theory and first order shear deformation theory include a geometric nonlinear panel analysis, where we can this analysis can bring tell us about the stress stiffening effects. It can depict also snap through in certain panel configurations, and also we can go into post-buckling area and get quite good results, as we have compared to some of the studies done on such panels. Earlier I mentioned about the possibility to define the statistical data for material property, and this data can be used then in performing probabilistic laminate analysis, so that certain selected material properties the properties are varied, and also we can give statistical distribution for loads, and also give some tolerance for layer orientations, and we can have any number of these parameters which for which we consider the scatter, and then we look at certain end property of a laminate, let's say stiffness in certain direction, or strength, or thermal expansion coefficient, and get the statistical distribution for that, or maybe more practical to say that what is the probability that the stiffness, for instance, is at least a given value. So as we know, the scatter in material properties is high in composites, and this kind of study can give good insight to what are the properties that we can actually expect from the for the end product. We have also capabilities for composite pressure vessels. This is an FE analysis, either shell or solid, using shells or solids. And the input for defining the fiber paths in the pressure vessel, it comes from a filament winding simulation software that we interface with. Free edge analysis, one of the exotic analysis capabilities we also have. Once we have an laminate defined in ESACOMP, it's also possible then to export the associated layup and material properties into different FE software like OptiStruct and Nastran, Abacus, ANSYS, LS-DYNA. So what ESACOMP does is it writes the input deck in the native format of a particular FE software, and this can be then added or appended to the input deck performing the FE analysis. And For the laminate layup, of course, it's relevant if you do zone-based modeling, or but then also ESACOMP can be just one might only want to use to apply properties from ESACOMP, but that's of course also possible to bring the apply properties and then do the modeling in the FE preprocessor using, for instance, apply-based modeling. For post-processing, utilizing ESACOMP, we have an interface with HyperWorks, where the results of the FE analysis are, and also the materials and layups are imported into ESACOMP, and we can then utilize ESACOMP in performing the failure analysis with all the different options that we have. And it's further possible to export the results and then be visualize those in HyperWorks with not only the reserve factors, but also get a visual indication of the failure modes and critical layers and at certain elements. And further, it's possible to then have a look at certain locations of interest within ESACOMP and have a close look, for instance, on the using fluid thickness plots. Currently, OptiStruct and Astrand are supported with this post-processing interface. It's always good to understand what our customers actually use ESACOMP for, and this is what we learned from some of our aerospace customers. So what they use is the composite materials database of ESACOMP. So they can the customers may be entering their own qualified material data in ESACOMP, so that it will be easily available for all the analysis, including the using the FE export going to the FE solvers of choice. The our aerospace customers use ESACOMP as a classical lamination theory toolbox. Well, that's definitely the core of ESACOMP. So they compute ABD matrices, engineering constants, and so on, and then may, as said, they may export the materials and layups to FE codes. The ESACOMP failure analysis are extensively utilized in the design validation. So the FE solver and its post-processing capabilities may not be what the customer needs. So for the detailed stress reports, ESACOMP may help in getting the reserve factors, margins of safety, for instance, with a given failure hypothesis presented in a way that's more suitable for the customer's purposes. And customers may be using the HyperWorks post-processing interface that we have had available for some years now, but also a lot of customers use their self-developed scripts for transferring the data. There's, by the way, there's a Python API for developing and integrating your own scripts and integrating ESACOMP in there as part of the design process as one tool. One way of using ESACOMP might be also in not in the standard design process, but also like for instance, when one needs to get a quick answer for an effect of manufacturing defect, and so the notched laminate analysis, we know that is being used by some of our customers for that purposes. We have recently released ESACOMP 4.7 version, and regarding the new features introduced in that version, the major one is delamination analysis for through the width type of delamination or debonding. So it's an analysis performed with shell elements and applying a virtual crack closer type technique. And basically at the crack tip, or we determine the strain energy release rate and use that as a criterion to define whether there will be crack growth taking place. So this is not an analysis to actually simulate the crack propagation, but it's a quick way of assessing if there is a certain size of a delamination to with a given load applied, whether this will be critical. We have also included enhancements for the HyperWorks post-processing interface in this release. Data bank updates, as we usually do in most of our new releases, and also documentation updates. The very important thing of the new version is that it's now under Altair's HyperWorks unit-based licensing system. This is a unique system where all the Altair HyperWorks tools can be used with the same licensing, with the same HyperWorks units. When you have a certain number of units, you can use all the Altair HyperWorks tools, which require not more than this amount of units. So it's very cost-effective system. You are not restricted to deciding which tools to use. You just get all the possibilities and use them within the amount of HyperWorks units that you lease or purchase. The ESACOMP legacy licensing is also still around for a transitional period, but we are now in the process of converting the legacy customers into HyperWorks unit-based licensing, because after next year that will be the only option there is. If your company is already Altair customer and using other products but has not been using ESACOMP, you probably have the possibility now to use ESACOMP without doing actually anything. Just install ESACOMP and start using it. It requires, though, that you have a fairly new license file delivered during this year. If not, then you might want to discuss with your account manager to see if a new license file can be arranged so that you have access to ESACOMP as well. Now, one might of course ask, when ESACOMP is now an Altair software, what's going to happen? And well, for one thing, we continue with the standalone product of ESACOMP, but at the same time there will be full integration of ESACOMP-based capabilities in Altair's other tools, and primarily this will be within HyperMesh and HyperView, so on the pre and post processing side. So among the kind of capabilities that ESACOMP offers, or the technology behind ESACOMP offers, for instance, composite materials database, and then different kinds of laminate analysis to support pre-processing. Also, I told you about the post-processing interface with HyperWorks. This is of course not the most ideal way of doing things. So now that ESACOMP is an Altair software, we move more to the direction of where all this capabilities is very integrated, and there's no need to actually for the end user go through an interface and transfer data, or at least it's not visible to the end user anymore. That's the direction we are going. And also the HyperMesh has the so-called stress toolbox, which has included already tools for for structural elements made of metallic materials or homogeneous materials. And now with the capabilities of ESACOMP, we are extending these capabilities to consider also composite structural elements. Also, this works the other way around, that ESACOMP will start using, utilizing the technologies from other Altair software, and one already ongoing project is the replacement of the current integrated FE solver that we have in ESACOMP with Altair OptiStruct, which will, for instance, bring us much more powerful tool in doing the finite element analysis. Also, it's in the plans to. I mentioned that we have some micromechanics capability within ESACOMP, but we have also intention to start utilizing Altair Multiscale Designer for this purpose, so that one can easily compute homogenized material properties starting from fiber matrix properties. So to conclude, why use ESACOMP? Well, we think that ESACOMP is very good environment to explore possibilities in your composite design. It allows quick and easy access to many analyses and to perform trade-off studies in early enough phase in the design that you are, when you're not too locked with your design decisions yet, but you have a possibility to screen the different possibilities. We also think that the right tools should be used in the right phase of the design process, and it's not necessarily the most efficient way to always start with creating an FE model for everything, because composite laminate as such as a building block for the structure is already fairly complicated. There's lots of things that can be done beforehand on that level, and ESACOMP is the perfect environment for doing those studies in the natural environment. In doing composite analysis, there's lots of pitfalls in where missing a failure mode that could be a potential one in a composite structure and so on. And ESACOMP gives possibility to have a look at on different ways in the design, and maybe after doing the complete FE analysis, then having a look at some of the critical points and have a look at the potential failure modes and so on. And also, it's ESACOMP is very good environment for learning about composites. So I already mentioned that ESACOMP is widely used in the for educational purposes in universities, but also within companies. There's a need to train new engineers who are not familiar with composites yet, and ESACOMP gives a very good platform for learning the composites behavior. And also ESACOMP also goes so much in depth that even the most experienced composite engineers can certainly find new things by playing around with ESACOMP.